Okay, so this presentation is called Data Assimilation for Urban Noise Maps Generating by Metamodel. It has been conducted by Antoine Lesieur, Pierre Aumond, Vivien Mallet, Arnaud Can from the INRIA and the University Gustave Eiffel. So after briefly explaining why a metamodel is required and how to build it, I will explain and show how it is used for data assimilation purposes and the performance of the process. So from the point of view of an acoustician, a noise map simulator takes some data like noise emission sources in road sections, building distribution, weather data, and so on as input for a simulator, and gets as an output a distribution of noise levels across an array of reception points. So the operator might add some perturbation to the input data. For example, to see the hour-to-hour evolution of the noise levels, but with the simulation only, this operation will require too much computation time. So the metamodel solves this problem by making the computation time nearly instantaneous. Indeed, it reduces the computation to a linear combination of a reduced number of statistically relevant noise maps weighted with interpolating functions, W, as shown in this picture. The metamodel at M is then a short sequence of elementary operations. So in this video, you can see in real time the variation of the noise maps when the input parameters vary. Here, the input parameters are light vehicles and heavy vehicles rates of flow and speed, the temperature, the reflection coefficient, and the distance to the intersection. Okay. So the purpose of the data assimilation process is to estimate the real state of the spatial distribution of the noise level, x to the t, based on two sources of data. The simulated noise map or background, x to the p, which is the output of the metamodel with estimated input parameters p, and a set of observation noise level by sound level meters scattered across the studio area. So here, linear data assimilation process called BLUE for a base linear unbiased estimator has been used in this study. It is a linear combination of the background map and the observed data, which has the lowest error variance. It is based on the background and observation error matrices B and R, x to the A being the sum of the background map and the correction map, which is the matrix product of the difference between the sound level observation and predictions at the observation point, and the matrix K will depend on B and R. So the matrix R is diagonal since the observation error are supposed to be uncorrelated. The matrix B is built assuming the further 2 points are, the less correlated they are. The further the estimated noise level are, the less correlated they are, as shown with the exponentially decreasing component of the covariance matrix. A statistical covariance matrix can be added to represent the correlation between 2 points induced by the low dimension of the metamodel, as shown in the second block. So this is the functional diagram which sums up the data assimilation process. The top of the diagram shows how the metamodel is built from a training sample. The bottom part shows how new input data is first used to create input metamodel parameters. The resulting output is then combined with the observation to compute the updated noise map. So this map shows our case study, the 13th area of Paris. The points are the location of the sound level meters used as observation points. So, traffic sensors observe the flow rate and speed of the vehicles on the major roads of the area. The first term, tau bracket x, is the average of at a given time of the traffic data, and bracket tau x times d is the annually average data for the daytime, which corresponds to the unperturbed input data. The input parameter of the metamodel is then the ratio of tau bracket x and tau bracket x times d. So in this figure, we can see that the output of the metamodel at an observation point is in red, fairly reproduces the observed level, noise level, which is in blue. So in order to test the performance of this method, leave one out cross validation is conducted. The data assimilation is conducted without a selected sensor. Then the resulting analysis of the removed point is compared to the observed value. The bias is stored and the process is performed for all the observation points at all the time steps. Here the results are displayed, bias and root mean square. We can see that the bias is more centered after the assimilation and that the RMSE is reduced by approximately 30% once the assimilation is conducted. Taking the statistical covariance matrix sensibly improves the performance of the process. Again, the performance is shown here, where the point with less than 2 dB error go from 42% without data assimilation to 56% with data assimilation with the statistical covariance matrix taken into account. So here you can see how the noise map evolves with the variation of the observed points in 24 hours. So the bluer the points are, the more negative the error is, and the redder the points are, the more positive the error is. Then you can see here the correction, how the correction evolves as well. So here we can see that where there is a huge difference between the observed and predict points, the error is propagated across the road network, and the same if the error is negative. Okay, so thank you for listening.